Hello, everyone. Thank you for joining the content routing track. My name is Massey from the Network Indexer team. In this talk, I'll provide you with a quick overview of what the Network Indexer is, its journey over the past 8 months or so, and its state today. So what is a Network Indexer? You probably have seen the Filecoin system map in Juan's previous presentations. If you look closely, Network Indexer falls right at the core of this map. It integrates with storage providers to advertise the content they store and offers a simple API for retrieval clients to find that data. So to put it more concretely, given a SID, Network Indexer finds providers of data associated to it, along with a list of protocols over which the data could be retrieved. So it's pretty simple. Diving a bit deeper, here's an overview of data flow in Network Indexer. On the left-hand side, you see index providers. They're responsible for continuously maintaining the list of SIDs that they provide, structured into a chain of advertisements and multi-hash entries. This structure effectively captures a historical diff, if you like, of the changes in the provided content, which providers are ultimately responsible for maintaining. Having this historical view allows the network to reason about things like accountability in comparison with a fire and forget approach, for example. As the content on the provider side gets added or removed, they then announce the changes to the chain of advertisement to the network indexers. This announcement is sent over HTTP or Gossip SOP. Once the announcement reaches a network indexer, the node then passively fetches the advertisement chain along with its multi-hash entries. It's important to point out this passive interaction here. The passive interaction allows the indexer to avoid being overwhelmed in a case where there are a lot of changes in the advertisement chain, while enabling it to collapse multiple fetch calls into one and transport unseen advertisements in bulk effectively. This is important when it comes to things like scaling the ingestion of advertisements. On the retrieval side, the interface to look up providers is pretty simple. It is a HTTP GET API that, given a SID or multi-hash, it returns a list of providers. Along with this thing it's called metadata. And the metadata is the thing that captures the protocol over which the data could be retrieved. The kind of metadata you see out there right now is largely made up of two kinds, which is BitSwap and Filecoin GraphSync. However, it is important to point out that the primitives are there for any custom retrieval protocol to be engineered. So for example, you could engineer your own custom HTTP API to retrieve information. The reason this is important is because it is designed to be extensible in that it allows the retrieval ecosystem to design the retrieval protocols that fits the need rather than being limited to parameters of just one design. Looking back at the past 8 months or so, honestly, it is incredible to see the progression and how far the network indexer has come. Early this year, there was about 30% chance of finding content on the network, with lookup times being pretty slow. In April, we'll launch the first version of the network indexer in production called SID.contact. At the time, this was the only production-ready indexer endpoint. Around the same time, with the help of Lotus team, we also integrated the indexing protocol into Lotus release 1.15, which allowed the storage providers to emit advertisements. By August, SID.contact have ingested over 8 billion SIDs, with great impact in improving lookup success for content hosted by services like NFT Storage. This improvement in lookup success was from about 4% to 96%. By the way, if you haven't seen Alan's talk on this earlier this year on IPFS Think, I highly recommend looking that up. We also worked really closely with the IPFS stewards to integrate Network Indexer into Hydra boosters. So around August, we started testing with the test environment in the Hydra boosters. Fast forward to today. The staggering amounts of SIDs have been ingested by the Network Indexer at the rate of about 7 billion per week. There are 6 independent partners that are also running network indexers in addition to SID.contact, and production Hydra boosters are fully integrated over Reframe protocol, which is amazing. Diving a bit deeper into what the network indexer looks like today, I've prepared for you an overview of SID.contact deployment topology. At its front, SID.contact heavily uses HTTP caching. So over 95% of requests are currently served from cache. We receive on average around 20,000 requests per second, peaking just under twice that amount, so about 40,000 per second, peaking with response latency of around 80 milliseconds. Requests that are not served from the cache are then sent to a custom-built load balancer / aggregator service, which we call Index Star. Index Star is built to scatter requests across multiple indexer nodes, gather the results, and then combine them depending on the protocol that instantiated the request. It is resilient against things like fluctuation of response from the backend nodes, as well as partial downtime of the backend nodes. It also maintains a persistent connection to each of the nodes. All of this combined together allows the Index Star to respond to queries within 4 milliseconds. This is something that we are pretty happy with. And finally, on the backend, we have independently deployed indexer nodes running Store the Index, which handle the ingestion of advertisements as well as handling the find requests. The thing to point out here is that these nodes are made independently deployable on purpose. This is to allow us to experiment with things like different configuration parameters as well as different backing stores, and help evolve the system in order to scale. The independent deployability of these nodes, coupled with Index Star, effectively gives us the freedom to break things in production, which is always extra fun, while minimizing the impact on the quality of service and end users, of course, which is fantastic. Here we have a rough overview of the cumulative distribution of advertisements and entries across providers. By distributions, we specifically mean here is the depth of advertisement chain and the number of entries or multi-hashes that are contained in them. We see a small number of providers with order of millions long advertisement chain. These are providers like NFC Storage, for example. And then, of course, there's it's predictable that there's a long tail of distribution for providers with smaller length and a number of advertisements. Here we have a percentage of Filecoin deals and storage providers that are covered by Network Indexer. Just under 30% of Filecoin storage providers are now advertising their content, which is fantastic, with around a quarter of Filecoin deals already indexed and discoverable by Network Indexer. So if you know the SID, you can find the provider and download the data. So over the coming quarters, we are looking to significantly increase these numbers, but it's just fantastic to see the uptake and the growth of data coverage. I thought I'd show you a graph of find request distribution on SID.contact. Here, this is the hourly distribution of find requests over SID.contact. You can sort of guess where the Hydra boosters were integrated with Network Indexer. This was about mid-September. As you can see, the rate of requests that we're receiving on SID.contact since fluctuates quite a bit. Thanks to the great collaboration that we had with the IPFS stores team, we've made a whole bunch of optimizations in the routing mechanism from the load balancer right up to Index Star and the nodes themselves in order to keep this lookup latency low despite fluctuation of requests, which is fantastic. That's it. Thank you so much for listening. Please don't hesitate to reach out to us on the usual channels. You can find us at Store the Index channel in Filecoin Slack.
I'm Tony. I'm going to talk about the state of delegated routing and the things that you can do with it. So there you have a QR code if you want to follow up with the slides, because there will be some links, and maybe you want to do some deep dive into some of the content in there. So what is delegated routing? So delegated routing, it's basically a way to be able to find content by the CID or to provide content to other peers to be able to find that content eventually. Also, you can find peers for their peer ID. It's also a useful functionality. And you can also set and get IPNS values on it to be able to have like content that will be evolving. Right now, the only routing system that we have, or the default one, is the DHT. And it's basically the default that we had on IPFS since a long time ago. But right now, maybe we want to delegate that routing system to other different applications. So why should we use delegated routing instead of the DHT? So mainly, you want to use that to do some experimentation. If you want to figure out different ways to the routing system, how to store CIDs, how to retrieve them in different ways, you can use that delegated routing API. Also, if you want to have responses in less than 10 milliseconds, you cannot do that on the DHT right now because it's basically impossible because you will need to do several hops to be able to find the content. Yes. So you can also have data locality. So like a CDN, you can cache the records nearby the users to make possible that speeds. And also, you can connect to other networks, like the Filecoin. So you can retrieve content from other networks like Filecoin. That is something that is not possible right now with the DHT. So we had some previous work. That's called peer routing for the GA's IPFS implementation and content routing. The problem that we had with that previous work of delegated routing is that it was super dependent on the kubRPC API, and it was not doing only content routing, but caching, providing records, and so on. So it was a mix of different concepts. And also was you needed the DHT to make that delegated routing API works. So the things that we have been building here. So as Will said before, we have the indexer integration. So basically, the Hydras are talking with the indexers to be able to retrieve content directly for the indexers instead of getting another methods to do that. And also, indexers are talking directly to the gateways to get faster that routing information that we need. Kubo is also implementing delegated routing using the HTTP API since the version 0.14. Yeah, there you have the documentation to be able to configure Kubo to make use of some delegated routing endpoint and use it directly on Kubo. This is our actual implementation in Go that is implementing the HTTP API. And you can use it if you want to do your experiments or to implement any content routing that you need. You can use that API directly. You have there the HTTP server and client implementations, and it's really easy to use. As I said, Store the Index is also using the content routing API, and it's storing, it's accessing to content stored inside the Filecoin network. Also, the Hydra boosters are sharing content from the indexers using the DHT, and you can communicate everything together with the delegated routing. And SOMGUI is a proof of concept that is basically a delegated routing endpoint that is implementing, it's getting the records from different other routing systems like the DHT and the Store the Index. So you can delegate the routing to that SOMGUI and ask for directions. And it will ask to different routing systems to find the content that you want. So some work that we can do in the future. So different ideas that we can implement using content routing is we can implement some thin clients. So you can have a really light client using the content routing API, and you don't have like a super heavy payload working in the background trying to get peers and get information about CIDs and everything. You can delegate that routing to other system and remove that that load from your system. Also can be used in content routing hints. So you can give to the user a CID with some hints about where the the data is. Maybe can be a content routing API, so you can ask directly about that content instead of trying to find that content in the whole universe of CIDs. And you can discover routing out of band, like using PubSub or any other method. We are still doing some research on it. And also you can do crazy ideas like implement your content routing over other peer-to-peer network like the BitTorrent DHT and experiment with this.
I'm Gus. I'm a IPFS steward, a Kubo maintainer, and I also maintain the Hydra boosters, which are an important part of the DHT. Yeah, so overview of the DHT. It's basically a decentralized database that stores records about who has what data. So like if you take a CID and you're trying to find who provides that CID, you'll extract the multi-hash out of the CID and look it up in the DHT, and it'll return you like a list of peer IDs of people who might have it. Once you have that peer ID, you can't connect to a peer ID. You've got to have an address. So there's another lookup in the DHT to map a peer ID to a set of addresses. And then the third thing that the DHT stores is IPNS records, which IPNS is like a mutability layer on top of IPFS. So you can have records that map names to CIDs, and you can update them. So we ran some analysis a couple of months ago on the DHT to find out like what the geographic distribution and the autonomous system distribution was across the DHT. So when we ran this, we found around 40,000 DHT servers across 150 countries and 2,700 autonomous systems, which was this like autonomous system distribution was way better than we thought it would be. So that was quite exciting. It was like we expected a lot of cloud nodes, but actually it turned out that most of these autonomous systems are not from cloud providers. But of the cloud providers, this is a breakdown of how popular each one of them are. We did this by just like looking in a database that had known IP address ranges from cloud providers. And again, we were pleasantly surprised by how heterogeneous the network was in terms of cloud providers. Hydra boosters, which have been mentioned a couple times, are they're DHT nodes, and all they do is they store DHT records, and they share a backing cache, but they're exposed as lots of peers in the DHT that all share the same backing cache. And the rationale for this is that since they all share the same backing cache, you're very likely to hit a Hydra node when you query, and if you hit one earlier, then your content resolution time will be a lot faster. Current likelihood of hitting a Hydra node during a DHT query is somewhere around 97%. It fluctuates with the size of the network. And as mentioned earlier, also they currently act as a bridge to the indexer network. So it was kind of a way for us to get the indexer records onto the DHT without having to push code changes to all the clients in the DHT. Hopefully, in the long run, we plan on removing that. And in the long run, we don't even want the Hydras to be around at all. They're sort of a technique we use right now to make content resolution faster. So we're doing a lot of analysis now to find out like what the long-term plan is for these. But while we have them, they produce very useful metrics because we get like a sort of a bird's eye view of the DHT. And this is a graph showing like the traffic that the Hydras serve. Like at peak, they get around 100,000 requests per second, which is very high. Another important component of the DHT is the client implementation that's used. So Kubo has two different client implementations. One of them is like a standard Kademlia client, which discovers the network topology as it queries. And the second is I call full RT, which stands for full routing table. So this crawls the entire DHT network up front and caches all the nodes in the DHT. And then when you do a DHT query, it doesn't need to ask anybody about where the provider record will be. It knows without doing any queries. So it's much faster, but the downside is you have to do a crawl up front, which can take like 5 to 10 minutes and has been known to crash home routers and things like that. But it's really useful for servers like that are running on beefy hardware where you need really high performance. You can also, like, because you know the destination of records when you're adding content into IPFS, like bulk adds of lots of data can be really, really fast with the full RT client. Obviously, one of the problems is you gotta cache every node in the network. So obviously that doesn't scale very well with the network size. And yeah, you have to wait many minutes before you can even start using the DHT. So Molly showed this graph the other day, but this is a graph of the resolution time in the DHT over the past year. So we've been making a lot of improvements to it. You can see that it's gone down from at a peak of like 1.3 seconds on this graph down to around 0.4 seconds. Many years ago, it used to be on the order of like 20 to 30 to 40 seconds. But as Will mentioned, 400 milliseconds is still really long if you're loading a web page. So that's where the indexers come into play. If you're interested in more measurements and analyses, you scan this QR code and it'll pull up this slide and you can click on these links. We have a whole team of people that spend all their time collecting data about the IPFS network and writing reports. I'll give you a second to scan it. So what are like upcoming work on the DHT? We've got a change about the land called Optimistic Provide, which is going to dramatically speed up the time it takes to add records or add data to the IPFS network. It brings the add time down from around 27 seconds down to like less than a second, which is a dramatic improvement. Should be landing within the next month or two. We've got another project to upgrade the DHT to improve its privacy so that if you double hash the keys in the DHT, then when you send queries to other nodes, they don't necessarily know what it is that you're looking for. We're going to keep doing more measurements and analyses and writing reports. And we're also working on a process for making protocol improvements to the DHT. So for a long time, the protocol hasn't changed because it's very difficult to upgrade the network. So we're trying to figure out a sort of process we can put in place to upgrade the DHT so we can start making some progress on these. So yeah, thank you.